Right. So I'm going to be talking about this theme, entanglement topology and tensor networks, and the slogan ER equals EPR due to Susskind and Company, which says that entanglement and wormholes are related to one another. But before I go into my slideshow, which is kind of simple-minded, I thought I would show you what happens if you go searching on Google and the archive on this topic. So this is just a record of my of a search I did yesterday. Oops, that was not a good idea. Sorry, I don't want both of these on the same setup. So one moment there. All right. All right. Still looks like I'm missing one. Just one more time. Well, I take what I can get. As I said, this is what would happen if you made a collection of things from the web about these ideas. And so here, this is a nice slide, which you'll probably find more than once. And it asserts that the fabric of reality might be woven from quantum entanglement. And then it shows a wormhole between two different locations in space-time, as you see. And it reads, wormholes connecting two black holes in different parts of space-time can exist, but only if particles on the black hole's surface are quantum entangled. If you break the entanglement, then the wormhole snaps too, suggesting that entanglement is the thread that binds space-time together. This refers to certain papers of Susskind and other authors, and I am not going to try to give you the physical reasons why they assert such things, but I'm just showing you what you may find as you look at this. So, well, of course, you find pictures you want to. Here's another idea in a picture. Here's a black hole, but then there is the question of the Hawking radiation from the black hole. And this is where people like Susskind have been worrying about this for a long time because of the quantum information paradox. The information that's in the black hole can radiate out of the black hole by Hawking radiation, but is the information actually preserved? You would like information, total information, to be preserved if you're thinking quantum mechanically. And they have trouble with arguments about the information passing across the event horizon of the black hole. But then this idea, which occurs in their papers, is that the elements of Hawking radiation are connected or entangled with their corresponding elements inside the black hole. And those entanglements could be themselves wormholes geometrically interconnected between the radiation and the interior of the black hole. And then, for reasons that I haven't sussed yet, this geometry of wormhole connection to the Hawking radiation solves some of the information problems that people are working on. So you can get these ideas, and then you are going to have to do more work. I'm going to have to do more work. You would too, to see how it works in the papers, but these ideas are out there. And now just some papers come along. Oops, we don't want to read that paper, do we? And then you find that as people start thinking about this relationship, possible relationship between quantum entanglement and wormholes, then you have people thinking about quantum ideas and quantum channels and so on in relation to the geometry there. And then other pictures come in. And then this is one of the more beautiful artists' conceptions about the Hawking radiation in relation to wormhole connections into the black hole. I like this. I like this one. And then you will see many articles. Some of them are quite artistic, and this looks like someone is imagining some kind of mechanism, central mechanism in the wormhole. Interesting. And then you will even see it's quite common to think of superposition and quantum states in relation to the Necker cube illusion, somehow has always been. But then I was struck on searching yesterday to realize that people have been playing with the metaphor with entanglement as well, which is quite interesting to think about. You can examine this yourself, do a little cognitive experiment. Do these two Necker cubes seem to be linked in their state? When one of them flips for you, does the other one flip as well? Are they entangled? Or can you view one, and I seem to be able to kind of cross-eyedly view one in its right state while the other one remains in its left state. But that seems a bit unstable. So you could think of entanglement in relation to multiple Necker cubes. What else do we have? The Einstein-Rosen idea. I haven't said anything new from this slide. And then thinking about tensor networks in relation, you'll see that that's what I'm going to be doing. But you can think about tensor networks in relation to entanglement, and then there are ideas that come about there and more. Just a moment. As I said, this is just my half-hour tour through the internet last night. I like this this cartoon here. Did you ever wonder if the person in the puddle is real or you're just a reflection of him, and so on? This is John Bell, who was one of the deep original researchers about quantum entanglement, as you know. Here's another picture of that Hawking radiation wormhole idea. And this, of course, is probably an artist's conception of that black hole, which was a black hole form, which was in fact observed this way as well. And here's another one, an EPR pair and an ER bridge, and an old newspaper clipping about Einstein attacking the quantum theory. And here's that Necker cube again. Superposition is two Necker cubes possibly in different states, but entanglement, they want to be in the same state. And then perhaps you've written slideshows like this yourself. And here again, this idea of going back and forth between quantum networks, discrete quantum networks, and the idea of the continuous wormhole connection. How does that work? More Necker cubes. This is mine. I made this years ago. I call this the Necker register, and it's that same idea, but I wasn't thinking about it in terms of entanglement. This is a Necker register, a very nice thing for you to observe and get apparent information out of, except you get no information out of it whatsoever, but you get lots of different binary states depending on what you see. But maybe it gives you information about what's going on in your brain. So I wasn't thinking about this the same way they were, but it's an interesting thought experiment to play with the Necker register. Notice how they do line up. As you look along a line and one of them flips, then the rest of them tend to flip as well. Is that entanglement? Here, as long as we're playing with that, here's another one that I like particularly. This is a virtual Necker cube. Your mind is supplying the cube and then supplying the two states of the cube from nothing more than these little local suggestions. And then you see a picture from a paper where they're thinking about the quantum states in relation to, in this case, it was a paper by Susskind, I think, and this is just a standard kind of quantum network quantum diagram like the one I'm about to draw when I go into my slideshow. And then sometimes quite striking magazine illustrations. This is from Quantum. And we have two spinning entangled particles at the mouths of the wormhole. Well-known paper by Susskind, you might make note of that one. Right. I like this this one from another Quantum article. The magazine Quantum has lots of good artists working for them, and so their science articles are illustrated with very imaginative drawings. Here we seemed, the blackboard seems to have turned into a black hole, as you see. Well, that's what will happen. And you see, I think it's quite interesting if you go in the surface of things like that, and go looking to see what you get some hints about what you should be looking at in order to penetrate some papers and lots of other misdirections as well. So here we go with my slideshow. I'm not going to do anything very complicated. I'm just thinking about these ideas. And Susskind's hypothesis, which starts out sounding complicated and then morphs into something which sounds like a topologist should think about it. And what it morphs into is non-locality and connectivity are really the same. That's the sort of thing he says. All right, and maybe one could think about that. Just thinking about topology. Maybe. Let's see what happens. So let me begin at the beginning with my my rant here, and let's see where we get. So I want to begin by talking about what is a tensor network. And if you do quantum topology in almost any form, then you're already familiar with tensor networks in the sense of quantum link invariants made out of local operators, maybe in a category for you, or maybe in a graph with some matrices attached to nodes in the graph. The idea of having a graph with matrix elements attached to the nodes in the graph goes formally back to Roger Penrose in his thesis in the 1950s, and is off and on taken up by various people, and probably goes back earlier than Penrose into Feynman diagrams and the like. But Penrose did articulate the idea of taking a tensor like this, X upper A, lower BCD, and turning it into a little node with some of its own diagrammatic geometry that you could remember it for, and then taking tensor equations like the equations of general relativity and putting them into diagrammatic form like this, and then also investigating questions about graphs and coloring and many other things by using the same kind of notation. And it's really quite useful to play around with this. So the syntax of it is very simple. In tensors, like this one doesn't have any repeated indices, so let's go to another slide. In tensors, you often have repeated indices like this. And I'm assuming you can see my pointer. Is that true? Can people see my pointer?
Yes.
Good.
Yes.
Okay. Right.
Yes.
So you have a lower index here and an upper index here. When you're reading it algebraically, one of the infelicities of tensors read algebraically is that you really need to know where the repeated indices are. Very important. You're going to be summing over the contracted index and so on. And identities involving tensor calculus involve learning to read this. And it's easy to slip because the D's could be very far apart algebraically. If you make a diagrammatic notation of this kind, the repeated indices always correspond to internal edges because a local node has an index and another local node has an index. Those nodes are the different letters in the tensor expression, and they are connected by an edge if it's a repeated index. So repeated indices become the internal graphical connections in the tensor network expressions. And this is one good reason for using them. And so we have this kind of formalism. Now I'll come back to that in a moment. Then there's the matter of teleportation. And teleportation is based on entangled quantum states, of which I've written an example here. This state is involved with two qubits that are tensored together, zero tensor one and one tensor zero. And what that means is that two different experimenters in principle could be observing this state, one after the other, presumably. We'll call the experimenters left and right. The left experimenter can find out about the left qubit in the tensor product. So left views this state and sees zero. Well, that means that the only possibility for right is to see one. It goes into the simple quantum state one when left views it. When left views one, on the other hand, it goes into the state zero. The second qubit is entangled with the first qubit in that way. And of course, when you make a measurement, it's probabilistic whether you're going to get 0 or 1 if you're lefty. So lefty doesn't have an obvious strategy to transmit information to right because of the probabilistic nature of what happens here. You might wonder, well, you could write a lot of different 2-qubit states. Which ones should really be called entangled? And it turns out, if you do an analysis of the algebra of it, what you really want for entanglement are states that are not just simple tensor products. So one of these alone, just taking this, is a simple tensor product of 1 with 0. But we can take more complicated tensor products, and we don't regard them as entangled. We regard a state as entangled if it cannot be decomposed as a tensor product of 2 single qubit states. So that's entanglement. And in this simple formalism, it looks particularly mysterious because there's no geometry, there's just the notion of quantum state. And you can imagine, nevertheless, that you have a little extra space information and that lefty is in Chicago and righty is in New York. And so when left makes his observation and finds a 0, he knows long before New York contacts him or he contacts New York that New York will definitely see 1 when they make their observation. So, and this is instantaneous. There's no transmission time at all between knowing that and knowing the other. It's simply a matter of knowledge. So people wondered for a long time, and many times, and still wonder, whether you could use entangled quantum states to transmit information. And eventually, and now I'm sorry, I've forgotten the authors of the teleportation procedure. I guess it's Charles Bennett and somebody else, but I'm sorry. A while back in the 90s, they figured out a procedure by which you could take a quantum state in Chicago and in principle transmit it to New York by using an EPR pair that connects Chicago to New York and a measurement in Chicago. And the way this procedure works is you make a measurement in Chicago of the twofold tensor product state of the left end of the entangled state and the state that you're interested in transmitting. You get this measurement, and now you know what's observable in New York. And you can figure out, if delta was very simple, that that what's observable in New York is going to be a certain transformation of phi. And if you set things up right, it could be a unitary transformation applied to phi. And you know which one it is. You know, because you made the observation in Chicago. So there might be four of them, a basis for the four-dimensional space of 2 qubits. So you have this little list, and you get on the phone or use your computer and send one of the numbers 1 through 4 over to New York, classically. And now New York knows what modification had to be made, and it was a certain unitary transformation applied to phi. So New York, without measuring, applies that inverse of that unitary transformation and gets phi back. And thereby, phi gets transferred from Chicago to New York. So you've transferred not only information, but quantum information efficiently, but using some classical transfer of information. A small amount of classical information had to be transferred in order to do it. No way to do it without some transfer like that. That's teleportation. And of course, I didn't go into the details of what kind of algebra you're going to choose to make everything work, but you see how the thing looks. Now, it looks like this, as I said, and let's see how that can be expressed in terms of tensor networks. Well, it looks like this if you express it in terms of tensor networks. The measurement that you make on the 2 qubit state corresponds to tying in the indices. This is a 2 qubit state, so it has like 0 and 1, or 1 and 0, or 1 and 1, or 0 and 0 for the basis elements, right? So there's a 2x2 matrix there. And the measurement results in a 2x2 matrix being applied to this. That I won't go into in detail, but there is a 2x2 matrix that gets applied. And here is the left end of the entangled state. And the entangled state also looks like a 2x2 matrix. That the state looks like a matrix is worth going back for. Here's my state. I say it looks like a 2x2 matrix. Well, in this case, it's got a 0, 1, and a 1, 0, and it's got 1 over the root 2 multiplying both of them. The matrix is 1 over root 2 in the 0, 1 place, 1 over root 2 in the 1, 0 place, 0 in the 0, 0 place, and 0 in the 1, 1 place. The matrix entries correspond to 0, 0, 0, 1, 1, 0, and 1, 1. A little 2x2 matrix corresponds to any 2 qubit state. And you'll notice that the matrix that I just described for this one, 0, 1, 1, 0, is an invertible matrix, unitary, in fact. So that's what I mean, that you can go back and forth between some of these entities and corresponding unitary matrices. So that's what happened here. And the E is some matrix. And then when we did the measurement and looked at the algebra of doing it, we ended up summing on this index J. And so we're multiplying the matrix M and the matrix E, the matrix for the measurement and the matrix for the entangled state. And then we're summing on I, which is connected up to the original state. So you see the original state has been multiplied by a matrix. And that's why I say it gets multiplied by a matrix. And if you know that the entangled state is an invertible, in fact, unitary matrix, and you set it up so the measurement matrices are also unitary, then a certain unitary transformation is getting applied to psi. And you, having measured, know which one and can tell that to New York. And that's teleportation. And as you see,
sorry, the matrix that you said was not unitary, or maybe I misunderstood which matrix you meant.
0, 1, 1, 0 is, well, it needs a 1 over square root of 2 to be unitary, but I'm not worrying about scalars.
So your matrix was a permutation matrix, or
yeah,
what?
it was a permutation matrix. 0. When I intone a matrix A, B, C, D, A is in the upper left-hand corner, B is in the right corner, C is in the lower left, and D is in the lower right.
So you got rid of your 1 over radical 2s.
Yeah, I'm sloppy about always saying the 1 over radical 2. Yeah.
No, but I know it's a small point of normalization, but like in your vector, you had 1 over radical 2. So what's the formal procedure of going from a state to a matrix? Because, or are you saying that you will always get something which is unitary up to a scalar? I'm little.
No, I think it is taking.
I don't always get something which is unitary, but if it's entangled, I always get something which is invertible.
So you simply identify
in order to do
matrices.
The teleportation procedure, I set things up so that the entangled state is going to be a unitary transformation.
If I understood correctly what you were trying to say, you just said that you identify tensor product with matrices. Basically, you just do the lowering of indices or whatever on one of the sides. But I'm not sure what it does to 1 over radical 2s. Are you just saying that if you take the entangled states with A, B, C, D and put A, B, C, D in a matrix, that you sometimes will get a unitary matrix up to a scalar? Is that the claim?
Yes, that's all I'm saying.
Oh, okay. Yeah, thanks.
Yeah, okay. But the main point that I'm making is not worried. I'm not trying to worry you about individual details about the matrix construction. I'm just saying that you can think about the form of the entire procedure as happening through a quantum network, through a tensor network. Okay. And so what I want to, so then when you're using tensor network to indicate the way you think about this, then you are using topology in an implicit way. You're saying left and right are connected not just by the fact that you can travel from Chicago to New York, but that there is this quantum connection via the EPR state, which is connecting left and right. So, so if we were going to play with and understand that I'm just playing with those ideas, then we could augment the original space, and this horizontal line represents the original Euclidean space, with a bit of network. We could attach the quantum network at one end and at the other end and make a new topological space. So I'd like to do this in a kind of least way and then think about the ideas. So I'm going to form a new space corresponding to my network by adding 1 point and some open sets. 1 point for the edge of this graph. So I am not adding graphs in the sense of each edge in the graph is a real line segment. I'm adding graphs by adding a point for each edge in the graph. And I'm going to take a neighborhood of that point to be the 2 endpoints that are abutting to it in the graph. So I've added 1 new point to the space and 1 least neighborhood of that point consisting of L and R. And I'll call that the augmented space. And then And then you see in the topological space, I've introduced a bit of non-locality, because in order to have a neighborhood of E, you have to have both L and R together. And I'll call that the quantum tensor space associated with it. And we could do this entirely for the whole network. But then there are some analogies that are worth thinking about. The analogy with the Einstein-Rosen bridge or the wormhole here is that now Alice and Bob, or left and right, can meet only if will meet through E. And even if the original space was disconnected, they're connected through E in this tenuous way that could disappear. So let's think about this a little bit and see if we go somewhere. A topological space is connected means that it's not the union of two open sets that are disjoint. And if I let H of X be the collection of open sets in the space, and I define tilde U to be the interior of X minus U, then I have a kind of negation, tilde, from the open sets to the open sets, because interior gives me an open set. This defines a hiding algebra negation on H. I won't worry you about the full definition of a hiding algebra, but I'll show you a characteristic feature of a hiding algebra in a moment. In a hiding algebra, you do not have the law of the excluded middle. And you don't, as you see. If you take tilde U union U, you remove the frontier of tilde U and U. And so there's no reason for tilde U and U to add up to the entire space, and they don't. For example, if I took the interval space from 0 to 1 and took the half open interval from 0 1/2 to 1, then tilde U is equal to V, the other half open interval, and U union V is the whole space minus the point 1/2. And if we took the union of U and V, that's everything but 1/2, then tilde of W, U union V, is empty, because you take the complement, which is just 1/2, and you take its interior, which is empty. So you have tilde W is X, which is not equal to W. But you have tilde W is equal to the empty set, which is equal to tilde W. And this is a characteristic feature of the hiding algebra situation, that a triple negation is equal to a single negation, but double negations are not necessarily happening in the sense of taking you back to where you started. So if a space is totally disconnected, then the hiding structure is Boolean. For example, if you had L and R, two disconnected points, then the topology consists of empty set consisting of L, set consisting of R, and both, and you have a little Boolean algebra there. And if you had a disconnected space like U union V with U intersected with V equal to empty opens, you could add one point like I did and declare that U union that point union V is the smallest open set in the new space containing P. And then the disconnect of X is joined by P, but the hiding algebra is now non-Boolean. So there is this dialogue between connectivity and hiding algebra that's basic in topology, like that. So we have the following notions here, that topological connectivity corresponds to non-Boolean hiding structures, and you can think of it in relation to quantum non-locality in the ways that we've been indicating. And so I think this is an interesting small circle of ideas to think about in relation to these physics assertions about quantum non-locality and connectivity. So we've added quantum networks to given spaces, and more complex geometric additions such as surgery, wormholes, handles, and so on can be thought about. But whether you should think about things like this as being limits of quantum networks that get more and more complicated between the two places, or whether you should think about it some other way, that's an open question. And involves going back and thinking about, well, why did the physicists say that quantum entanglement between these 2 points at the mouths of the wormholes was necessary for the wormhole to exist altogether, and all of that background that I indicated to you but didn't go into. So this talk is about some preliminary foundational thoughts. Another foundational thought that's worth bringing in is that when we do topological quantum field theory, we think of a cobordism as corresponding to a map of linear vector spaces. So we go from something of manifold topology and go directly over into the essentially discrete world of linear algebra for quantum theory. And so if I had a wormhole like this, arrayed categorically upward like that, then I would think of mapping from the complex numbers into V tensor V, where V is associated with the loop of the wormhole or the mouth of the wormhole. And that could be some quantum state, some entanglement between the ends of the wormhole. So it's natural to think of entangled quantum states between the ends of the wormhole in that sense. But there you make a jump by speaking of a functor which goes from cobordisms of manifolds over to linear vector spaces, a big jump from the continuum to the discrete. And there are lots of natural ways to think about that jump. And so some of this is related to that. The quantum network could be modeled back here by manifolds if things were fitting into patterns of this kind. Another idea related to this is what happens when you measure. For example, suppose that we're looking geometrically at this space. Here's ordinary space augmented by an EPR pair from New York, from Chicago to New York, and from New York to Paris. And in New York, someone makes the measurement of the two ends of this of these two quantum states. Well, then they become linked up with one another. The measurement in the tensor network, as you see, creates a new matrix which goes here through M and then through the matrix of E all the way over to Paris. So the measurement changes the topology from the point of view of my construction. It doesn't change the base topology of the original geometric space, but it changes this more malleable or flighty kind of topology of the quantum network that's attached to the space. And doing this kind of measurement is called entanglement swapping in the trade, because you see, that's exactly what could happen. You could make a measurement in New York, and now you have an entanglement that goes all the way between Chicago and Paris. And you might do teleportation coupled with entanglement swapping and other quantum procedures like that. So it's interesting to think about the topology of these spaces in relation to measurement and how their topologies will change in relation to measurement. Now, this part is just describing what I said about networks, so probably no need to bother with that part of the slide. On the other hand, when you put matrices into the network, the matrices may have some nice properties, like this is a favorite one of mine. If I had a projector matrix that was attached between 2 points of space like this, this projector is a specific one that you can play with. If you just multiply formally and delta is the value of a little closed loop, then you'll find that the product of this guy with himself is equal to himself. But you could just take it as axiomatic that you have a matrix whose square is equal to itself. And then if you had a matrix in a line in your network, well, you could multiply it up. you could have as many as you like. You could go to infinitely many if you wanted to. And the topology will be changing all the while. More and more points are coming in every time I put one more of these in. And you can think about the limits of the topologies I've described in relation to continuum and so on. So there are some thoughts there about how continuum might arise out of the discrete. So as I said, we've shown how to augment a space to a new space containing a topological version of tensor networks that describe its quantum structure. And this marks the beginning of some unification of properties of spatial connectivity and properties of quantum entanglement. And so those were the, this is where I'm playing around with this at the present time. And I thank you for listening to that. Questions?
And is I guess the mapping is invertible, right? To when you're adding more and more points to the, to basically form a continuum.
You mean I could remove a point?
No, I was
You're
just
thinking of, you're thinking of, I have a space, I have an ordinary space, and I'm adding this tensor network points to it.
I was kind of comparing like the wormhole with the tensor network, that like the simple one that you showed, for example, when you have one E that was entangling two states at the ends of the wormhole. I was kind of comparing it to how in topology, when you're building simplicial complexes to represent a particular topology, this would be like a, a one simplex that's sort of trying to capture the part of the topology of the space. Of course, it's not capturing the whole structure of the wormhole, but I was wondering if similar to that, you can add, you were saying in the end that you...
Oop, you froze.
Yes.
I'll give it a moment. We aren't completely frozen. There you are, you're back. Okay, you froze for a bit, so you need to repeat.
Yeah, I basically just saying that I guess the movement back and forth is invertible, right? Adding points.
What do you mean, adding points or removing points?
Yes.
Yeah, I could just as well. That would be like imagining that the wormhole disappeared.
Yeah, or it could also be when you have the wormhole and you add more points there along the way, what would that do to the system? Would that mean that you are introducing more and more entanglement along the way?
Well, I went to the most extreme point set topological place, right? I added one more point, the least thing I could do to obtain connectivity. So the least thing that I can do to obtain connectivity between L and R is to make a neighborhood of the new point that contains both L and R. And then I have connectivity even if L and R are disconnected. So I think that that's, it's nice to go to an extreme that's very elementary when you think about it. And that's like the event horizon of the wormhole, right? That extra point. But all the rest is gone. It's just the smile on the Cheshire Cat. But how do you think about that in relation to the usual continuum wormhole? Do you want to think of the continuum wormhole as a limit of more and more complicated tensor networks? Maybe you do, or maybe you don't. I'm not sure. It might depend on whether there was a nice theorem about how limits of very simple topological point set additions could go to manifold topology, which there might be such a theorem.
Yeah, but it also reminds me of like this point that you mentioned at the beginning, and you were showing that figure from using the Mera state, this hierarchical hierarchically entangled state, and how people have found that you can directly relate that to geometry of the space. For example, an anti-de Sitter space, which would have this kind of negative curvature, can be represented as the limit of a hierarchical tensor network that just kind of looks like a tree.
Yeah, that's an enticing idea.
Mm-hmm. Right.
Oh yeah, in principle, I remember, maybe you remember on my talk about hyperbolic structures, and there it was that you have a network of a graph with some tensors and with some amplitudes. It was not unitary. It was SL2C, but like I use it for the to describe machine learning and such things, and there you can see if you the amplitudes in a network grow up, so the network choose special ways in a network, then you can describe or interpret it as negative curvature, and at the end, as in a limit of infinite curvature, the graph degenerates to a tree. And a tree is, in principle, after Gromov and such people, an hyperbolic space of infinite negative curvature. So a tree is such things, and that is where it degenerates. And that is maybe one example where it goes like in your direction, what you think about anti-de Sitter and tensor networks. And in your case, I have maybe one remark. I remember back on some papers which I wrote together with Georgie Crow about intuitistic logic and Heyting algebras. And the interesting point is that usually at first you need to define an Heyting algebra, you need a lot of open sets, yeah, to really define an algebra. You given the example, but the problem is now usually if you have a manifold structure, you can choose charts, whatever you want. But in the case of R4 or R3, you really have one chart, which is enough. But for more complicated spaces, you need more charts. And really to define Heyting algebra related with the topology, you need enough open spaces, which are not arbitrarily defined, but which are fixed defined, or we have a fixed set of charts. But
wait,
charts,
I'm not sure I understand what you're saying.
Okay. The point
if you
was,
take any topological space,
yes,
and you define that negation on the open sets, you have a Heyting structure on the topological space on the open set. So you're saying to have a Heyting algebra with certain properties that you want, I guess.
Right, but okay, from physics point of view, every chart is a system, or is in some sense. So it's a physical system. So at first, you of course you can start to say, okay, your space is built of, say, an infinite or countable infinite or a finite number of systems. Then you have this number of open sets which are covering and building the whole space. Okay, then I agree with you, and then you can define, of course, you have enough structure, you can define the Heyting algebra. But usually in manifold theory, one say, okay, everything is I have some charts, and I can add more or can refine the charts and I get more and more. But in principle, what I show in manifold theory is that the whole thing is independent of the choice of number of charts. You need sometimes a minimum, of course, but how many you have,
yeah.
depends.
So I think I begin to understand. I mean, when we're talking about a manifold, we're talking about it's diffeomorphism type, or it's type in
instance,
some form
type,
of manifold,
right?
And then if you went down to just its topology, you wouldn't be getting the manifold structure. Of course, you wouldn't. You wouldn't have told. So if you want to say the whole thing in terms of Heyting algebra structures, you might be able to do it by relating the charts to the manifold as a whole in different.
Right. And what we found was that in the case, for instance, of the R4, we considered, of course, the exotic R4. In that case, there's a big difference because the exotic R4 needs an infinite number of shards. And so automatically you have a Hiding algebra, and automatically you get also, the Hiding algebra is connected with distributive lattices, which defining projection operators, and you get then the connection to quantum mechanics. That was the abstract link, which one usually get. But to get this link, you need enough open sets which are not arbitrarily defined, which have some relation with physics systems, or which are fixed in some sense. Yeah. And then in the case of the exotic R4, you cannot cover any exotic R4 by a finite number of shards. You need always an infinite number, something. And so automatically you have enough states in the sense of quantum mechanics to cover the whole space. Sorry. That is what we found.
So in your view, when you're thinking about exotic structures in relation to this, the exotic structures may be telling you about limits of quantum nets.
Yes, that is, that was our idea, right? That is what I also spoke in the previous lectures. That I say, talks, wired embedding and is a quantum state is a wired embedding and such things. But in principle, that is what is the idea behind it. Very, very good talk to make this clear. It was not clear for me before, so I understand it more now. But that is my understanding now. Right.
What about using the handle structure to describe your Hiding structure? So you're not looking at all open sets, you're just looking at the critical region caused by the core and the co-core of the handle.
And you suggest that we might be able to define a Hiding structure directly from that, maybe?
I'm speaking off the cuff, but what you illustrated, what had to do with handle structures in very low dimensions. So if you try to move the dimensions up, then it makes sense to think about the handle structures as you're moving up, which is basically what Torsion was suggesting, I think, because he thinks about the exotic structure as this infinite sequence of 1 and 2 handles.
Oh, right, yes. Then you have an infinite number of cobordisms between handles. Yeah, right. That's okay. But you need a little bit extra structure. That is what also get. Usually you need principal disjoint, or can be also linked cobordism or handles in a structure, because you need to represent an entangled state. You need in principle, if on a level of cobordism, you need 2 cobordism. Every cobordism is a tensor product in principle, but the entanglement means that both cobordism have to see together. They're not enough to see it as a disjoint union, and that means they are in principle linked, the 2 handles, and then you have 2 cobordisms which are maybe getting your entangled state, right? That is what I. But right, Scott, that's a good point, right? The handles also, an infinite handle structures also works well in the same sense, in my opinion. Yes.
It's good motivation to go back and think again about what all those things that you said about quantum states in relation to fractal structures and exotic structures.
Yeah, or at least why it's or infinite handle structures. Yeah, something like that. Must not. I don't think one really always has to speak about exotic smoothness, but to have such an infinite handle structure. So then you have enough states, and they are linked, and they are, but non-trivial in some sense. So
right.
One of the other images that came when Lou suggested using the finer and finer tensor networks was thinking about it in terms of link homology, which is not
yes.
unlike the Handel structure.
Right.
Wait, what do you mean by that? You say link homology is not unlike Handel structure.
So you want to replace your single vertex with a large scale network, and then that large scale network is approximating what your tube is, and in that sense, it's a notion of link homology.
Oh.
And
You're thinking of something like a Kovanov category as a kind of
Right.
connection between the A state and the B state of a knot.
perhaps.
I'm
Yeah.
thinking of one end of the cube and the other end of the cube.
Yeah, right.
Ah, okay.
Is that the image you had in mind? You're thinking of the cube as a connector
No,
between it.
the image that I had was one that you drew, where you replace the tube with a network of matrices, and then that network of matrices suggested to me that it was some sort of that you were approximating the tube by a simplicial complex. And I guess in my own mythos, I don't think that simplicial complexes and Handel decompositions are that far apart, particularly in low dimension.
But the striking thing about the Kovanov category or other categories associated with link homology is that all the arrows go in one direction. So you have this arrow coming out of one point, and then a lot of them, and then it gets big, and then it gets small again, and now you're down to another point. So you have this very directed category like that whose homology you're looking at.
Right. So did I say link homology? I meant persistent homology. But your point,
so I got to associating in another direction there.
Yeah. But I think your association is also very pleasing. So they should both be contemplated.
Right, but the persistent homology is somehow very close to these ideas, because you start with dust. You start with something with a discrete topology, and then you begin growing little neighborhoods until they make connections.
Right. That was the image that I was getting. But who knows?
Right. Yeah. It reminds me also on operads and homotopy theory in these infinite loop spaces. Some of these pictures are also in your tensor decomposition on some of these ideas in that direction. But it's only it reminds me maybe only on that.
Yeah, thank you. Maybe this is a good place to stop. Thank you very much for listening and for discussing. We'll see what happens next week. And I will say goodbye. See you next week.
See you next week. Bye.